Welcome to Mastering Git. I am Tom Parkin. In the several decades that I have been writing software, I have used many different systems to keep my source code under control. Git is without a doubt my favorite, and I have invested a lot of time in becoming proficient with Git. Please allow me to share with you much of what I have learned about source control and specifically about Git. We will begin with an overview of version control, including a description of the two primary approaches. What is version control? When creating software, writing source code, the process is quite iterative. There are many changes that take place. As a project progresses, the code base grows and changes. This is the nature of software development as an activity. On larger projects, these changes are coming simultaneously from several members of a team of developers. Maintaining control of all this activity, managing the myriad of changes that occur regularly, and providing a means to access previous work is the essence of version control. Version control, commonly called source control management, which is a more descriptive name, is a multifaceted tool. Typically, it provides an active developer a way to save work, a way to collaborate with others, a way to communicate to others, a historical record of the evolution of a project, and a means to experiment or test ideas. A source control management system, SCM, is a database of changes. It tracks the changes made by different developers, will automatically merge changes, and can help resolve the inevitable problem when more than one change has been made to the same file or set of files. A naive approach to managing this sort of change involves saving multiple copies of similar files under slightly different and largely confusing names. This also prohibits any opportunity to locate a particular change made somewhere and sometime in the past. If we resolve to accept the many benefits offered by a source control management system, there are many popular choices. All of these fall roughly into two categories. The centralized system requires every user to be connected to a single centralized database. This is the master set of source control and provides a high degree of consistency. Since the entire project history, every change being made, resides in one central place, all changes must be reflected back to the master data set. Each developer must check in and check out the code they work on, thus prohibiting others from access to it. In a distributed system, there is no master or centralized system that houses all the changes. Git, which is a distributed SCM, is structured such that every user holds a copy of the entire set of changes, called the history. At first, this may sound ridiculous and quite difficult to manage. In fact, it is one of the biggest differentiating features of Git over other centralized systems. We will explore this in much more detail, but a few of the prominent advantages of this scheme are implicit redundancy, because many copies exist, one with each developer. Quicker, uninterrupted workflow, since each developer can be working independently without waiting for someone else to relinquish their lock on a file or files. Operations like diff and merge are much faster. All changes are being made locally. This also means a developer can craft the changes that will become part of the permanent history. More on that in Section 6. Branching and merging are a bit simpler. Extremely simple and lightweight in Git. Not tied to a central server, it can work when offline. Extremely simple to set up and get operating. This we will learn in the next section. Developers are more free to explore and experiment. With a local repository, you are not affecting others. Do not misunderstand. Being distributed does not preclude a Git repository from being stored in a central location, accessible to many developers. It is just not required with this topology. The simplicity of Git as a local source control management system that requires no special server is what has made it extremely popular for solo developers and work on projects that will not include collaborators. The flexibility that is derived from a distributed SCM, combined with the fact that it is free and open source, has made Git the de facto system for open source software projects. Teams of all sizes use Git to manage software projects like Node.js, jQuery, Backbone.js, Homebrew, Ruby on Rails, the Linux kernel, and even Git itself. We explored version control, otherwise known as source control management, and how it affects your ability to develop software. In the next video, we will dive right into using Git. It is time to begin our adventure with Git. Let's get started. It is assumed you have Git already installed. We are going to explore a free service that provides us easy access to Git. Then, a few commands to verify your installation of Git. Finally, we will set up some global parameters in Git. I want to share with you an alternative to installing Git. We will use a great new service called nitrous.io. And because nitrous.io provides easy access to work on these exercises anytime and from anywhere, it will be the way I demonstrate Git throughout the remainder of this presentation. Even if you have Git installed on your local computer, I highly recommend using nitrous.io to follow along. You will first need to create an account on nitrous.io. It is free and takes only a few minutes. Here is the URL for Nitrous. Create a username, enter your email address, and then respond to the registration email message. Next, you log in and create a new box. Select a region based on where you are located. I am in the eastern United States. You can give it a name or accept the random one that is provided. Click Create Box. We now have a Linux instance accessible from any browser, anywhere. If you are interested in a little more in-depth understanding of Nitrous, you can check out this video I created and posted on YouTube. In order to fully exploit the flexibility of this, and because this is my recent favorite, we will utilize the Nitrous method throughout this entire project. If you plan to interact with services like GitHub or Bitbucket, you will need to set up SSH keys. There are clear, concise instructions for that in the excellent nitrous.io Help Center. Next, we will verify you have Git installed and double-check the version. We can check on Git with just a few commands. At the command line, type git space -- version. I will do this on my Nitrous box. You should do the same on your machine or your Nitrous box if you prefer. The response indicates the version of Git installed. I have the latest available because Nitrous keeps me up to date automatically. Next, we will finish up the setup process. Now we will set up a couple of global parameters. This is the first thing you should do after installing Git. These are configuration settings that affect Git globally. We will not go into detail on all the settings, but the most important are user.name and user.email. These are important because they will travel with the repository, attached to each commit you make wherever it goes. You tell Git your desire to access global parameters with this -- global switch. Try this now along with me. At the command line, type git space config space -- global space user.name space and then your name. Then type git config -- global user.email followed by your email. Be sure to use double quotes around the values. We can use git space config space -- list to view the values we just entered. Although they only need to be set once, you should be sure to set these on your system as I have done here on this Nitrous box. Next, we can start using Git as we explore the typical workflow and look at a little more detail. Next, we examine the Git workflow very carefully. In this section, you will see quite a lot, and you will do quite a lot if you follow along. By the conclusion of this section, you will be well versed in how to use Git and how Git works internally. For the remainder of this presentation, you are encouraged to follow along. I am using nitrous, as I explained earlier. You are welcome to use whatever makes you most comfortable. If you are using Windows, be aware that the Unix command touch I use here is a shortcut to create a new file. You can use an equivalent technique like copy con file name and Control-Z to end and close the file. In this section, we will examine the Git workflow in detail. Let's set up a little Git repository to work on. We will create a directory for our practice. Call it packed. Then cd into that directory and initialize Git with git init. Now let's create a README file. Add this one line in the file, Mastering Git by Tom Parkin. We can advise Git that we want to track this file with git add and the file name. In this case, we could have simply used git add dot to indicate all files in the current directory, and then make a commit with a simple message like this. The command git log verifies our efforts and shows us where this commit fits into the lineage of this project. We will talk more about git log in an upcoming section. We will use this repository throughout the presentation. Now, let's take a look at the typical Git workflow. If you are like most people, once you have begun using Git and become somewhat comfortable with it, this is probably your standard workflow. Write some code, add some new files, commit all changed files with git commit-am and a message, repeat. And if your intention is to simply save your work, this workflow will suffice. We are here to explore a little and see many ways to leverage the very sophisticated features Git has to offer with the goal to improve your workflow. The added benefit is that you will be recognized as a Git expert and earn admiration from your peers. For example, the status command. I am sure you have used it quite a lot. A plain vanilla status will show a lot of information. It includes the files Git is tracking along with their status, that is, modified, deleted, etc., as we see here. These are part of the index. Those files in the working directory that are not included in the index are considered untracked files. We will take a closer look at the index in an upcoming section. There are numerous options available to refine this output from the status command. I recommend you experiment with these to find the combination that makes you comfortable. Personally, I like this combination, git status-sb. You will see me use this often. With this simple common workflow, Git can capture, preserve, and maintain a historical record of the changes you make on a project. But we can do better. That was an examination of a common workflow for Git. In the next video, as we better understand some of the intricacies of Git, we will look at the staging process. Setting the stage. In this video, we take a look at staging changes for a commit. Git manages changes, an important concept to always bear in mind. Follow along as I create a new file, and then we will commit this. But wait, what happened here? I said Git tracks changes, and this new file is certainly a change in the working directory. But we must advise Git this change, the addition of this file, is important to us. Those changes are captured and tracked in the Git index. The index contains a snapshot of the changes that will be applied in the next commit. Adding changes updates the index and is known as staging them to be committed. In the previous section, I indicated we could have issued the command git add dot, and changes to all the files in the current working directory would be added to the Git index, staged for the later commit. In older versions of Git, there was a subtlety here that confused many people. Using the git add dot to add the working directory to the index would add new and modified files, but not deleted files. That was changed with the recent update to Git, a change I welcome. Now you can add the --no--all switch to force that former behavior. I will highlight some other changes that are part of the recent update to Git version 2 in a later section. Let's see a few examples to better understand the real differences among these options with the git add command. Follow along with me. Still with our little packed repository, we will create a few simple files, one called changed file and one called deleted file. We explicitly add these two files to the index using the file spec. Let's examine the index using git status and now commit those changes. And look at the index now. That seems to make sense. Let's make a change. Modify a file and also delete a file that is already being tracked. We can see that Git recognizes the files that were changed and deleted. The file we added to the working directory is designated as untracked. But do not lose sight of the fact that none of these are staged for the next commit. Remember, Git is only working with changes. It is not merely maintaining references to files like some other VCS do. Furthermore, we must explicitly stage those changes in the index that we want captured in the next commit. In order to illustrate this, let's continue. If you use git add dot, as expected, everything is staged. Now, let's undo, take a step back, and try git add -u. Create a new file called git add. Notice how this captured those files it had already been aware of. Git realized I am actively working in these and want to keep my changes updated. But what about that git add file? We did not explicitly ask Git to track it. Now, one more experiment to illustrate another new change. In case it is not obvious, the reset is a handy way to tell Git, I changed my mind and want the index to be cleared. You can specify a file name if you need to unstage just the changes in one file. Finally, let's try git add -a, that is a capital A. I remember capital A as all in large letters, like I'm shouting. Notice how Git scooped up all the files we had in the working tree and added them to the index, even that one we created in the previous section. Let's make a commit. I used the -m simply to avoid opening an editor. It is a common shortcut. Finally, an important clarification to remember. The $A will add to the index all files in the working tree, whereas the -u is for update. Git will add to the index changes in files it is already tracking, no new files. Now that you have a clearer understanding of the index, you are better equipped to take advantage of these additional commands to control what is captured in a commit. As we have seen, the -u command will update the index to match the working tree. -I is used to selectively stage portions of changes. This is how we can carefully control the contents of a commit and ensure all related changes are committed together. If you have files of a type listed in your git ignore, you can add them to the index, overriding the git ignore by using the -f switch for force. Try to develop a habit of controlling what you add to each commit. This is known as crafting a git commit, a topic we will look at more closely in later sections. In this video, we saw details of the Git staging area, its index. In the next video, we will take a detailed look at the Git commit. The commit close-up. In this video, we take an intimate look at the Git commit, including the objects that are created to store a commit. The set of changes captured in each of those commits you performed in the previous section are now permanent. Git never forgets. A commit is really a blob of changes. It contains several key components. First, the set of changes and references to those files where the changes exist. Remember that Git is not tracking files, it is tracking changes to the content in files. A unique identifier called the SHA hash, this is devised based on the actual content. So for all practical purposes, this identifier is absolutely unique to this particular commit. When you think carefully about the distributed nature of Git, it becomes evident that this is essential. There is a commit message. This is the developer's notes on what, when, why these changes were made, and also who made this commit and when. And there is a pointer to the commit from which this one was generated, its parent. Back to our packed repository. Follow along. Edit the README file. We will add some text. Put your name at the top of the file, too. Now use git status and see that Git knows this file, which it is tracking, has been modified. Make a commit. Let's use the common format with -A to indicate all changes and M to add a message. As I explained earlier, this simplifies the message part by not opening an editor. The command git log now shows us all of the commits we have made so far. Add the --pretty equals fuller for one of the pretty formats, and we get a lot more information. Note that the hash on your commits will differ from what you see here, even though we have made exactly the same changes. Because each commit contains a reference to its parent, the entire chronicle of changes can be browsed. This is known as the Git history. Since we have a handle to the most current commit, known as the head, the checkout process can easily walk through the history, reconstructing the entire state by applying all changes. This is an intentional design which reduces the amount of data that actually needs to be stored in each commit, and it is one of the differentiating features of Git. The checkout process requires a reference to the desired commit in the history, and recall, each commit has a unique hash. This is the handle used throughout Git to reference a commit. Even patches, tags, and labels are just aliases to the underlying hash. Because we will use that hash so often, and because developers despise typing more than is absolutely necessary, you can always reference a commit in Git with only enough of the first part of its hash to be unique. By the way, the commit command is so important to the Git workflow, it includes one of the largest set of options available. The most common are -A and --amend. Here are a few more interesting modifiers. If you have been following along and there are no changes in your working tree, you should have nothing staged. In this video, we looked at the Git commit in detail. In the next video, we explore a bit of the behind the curtain in Git operation. In this video, we examine the Git directory. Follow along with another experiment. Let's create a new directory called Explore, and then cd into it. The directory is empty. Now, initialize a Git repository with git init, and take another look. Be sure you are viewing system and hidden files. In Windows, you need to add /a to the dir command. This is the hidden directory Git adds when you issue the command to initialize a Git repository. As a matter of fact, this is exactly all it does. There is no special magic Git uses. All the data is stored in the file system. Now, create a few files, make a commit, and then do that several times. Now, git log will show you have several commits. Let's explore a few of these hidden directories. All of the Git objects are stored in files at .git/objects. As we saw in the previous section, with the commit action, Git stores blobs for the changes, here in the objects directory. It updates the index, creates trees and commit objects, and stores them internally. We can peek into the organization of those blobs and trees using one of these special Git commands. This is not something you would normally use unless you are writing tools that interface with Git at a low level, but it is useful here to explore a bit. The cat-file command shows a list of trees and blobs. You may recognize the file names displayed. The hash is a pointer to the blob or tree that contains this data. You may ask, since the index is such an important part of Git, where is it stored? And that is a fair question. Let's take a look. In the hidden.git directory is a file named index, of course. Although its contents is binary, let's peek into it. In Windows, you can use the type command. I am using the Linux cat command. Among this garbage, I think you can recognize the names of the files we added. Now, add another file to the index, like this. Peek at the index file again. And there is a bit of the magic of the index. It is just a specialized file that maintains status on changes. However, as we learned, it will only track changes we specify. Another single file we can easily read is in .git at refs heads. It's the file called master, and it contains the unique hash of the commit that is currently the tip of head, the most recent commit to which we are pointed on master. Notice that it matches our most recent commit, the head. This is the place where the next commit will be added. A reference to this will be included as that commit's parent. The hooks directory contains a set of sample Git hooks. We cannot go into details on commit hooks in this series. I recommend you explore those and experiment in order to better understand how to implement commit hooks. We never need to dig into the internal plumbing of Git in our work as a software developer, but the important fact to bear in mind is that since Git is entirely file-based, it can be easily transported, stored, backed up. There is not a requirement for any specialized server to maintain a Git repository. In this video, we looked behind the scenes at the way in which Git accomplishes its magic. In the next video, we will look at the Git remote. The remote. In this video, we will examine the way in which Git, as a decentralized and distributed system, permits synchronization of repositories across multiple users and multiple machines. If you are working on a team, you may need to access some work of a colleague. You will often get a Git repository from a service like GitHub or Bitbucket if you wish to participate in open source software development. There are 3 common commands to get a Git repository. They are clone, fetch, and pull. Your habit may be to use one of these all the time, probably pull. But understanding the specific behavior of each will give you more control over your workflow. Use clone when you want to establish your own copy of an existing Git repository. This command creates a new directory using the repository name, establishes the upstream remote tracking to keep you in sync with the source, and then checks out the active branch, which is usually master. By contrast, the fetch command simply brings in any parts of a repository you don't already have, but it is left for you to decide if and how any of those differences will be merged into your current work. This is the way in which you capture changes others have made to evaluate before merging them with your work. With pull, Git will internally execute a fetch and then attempt a merge. This means it is possible to get a merge conflict as a result. We will look at merge and merge conflicts in detail a bit later. With pull, you can specify only a particular branch from the remote repository if you wish. When you wish to push your changes to a branch, but someone else has already pushed before you, you have to pull in their changes first. Normally, Git does a merge commit in that situation. In many cases, you will use the HTTPS protocol, and when pulling from GitHub, for example, the properly formatted URL is just a click away. There is another proprietary protocol Git supports that is built on secure shell SSH. So if you have SSH keys set up between the two machines, you can use the Git protocol. This network-based protocol allows easy reading and writing to Git repositories. It is important to note that you can also use the internal Git protocol for getting repositories from other directories on the same machine. If your entire team has access to the same shared drive, this is a trouble-free way to share the repository. There are a few simple commands to set up your remote repository stores. It is important to be sure that you have appropriate connectivity, and if you are pushing, you need the proper credentials, even if you are just interacting with a colleague's machine. In the common case, though, where you will pull or fetch and then push back to the same location, this is all simplified with the git remote add command. I had difficulty remembering the proper syntax for this command and developed this mnemonic. It requires a name, you give the name, and the URL of the other computer. It may seem a bit simple, but I remind myself that name is before URL alphabetically. That is how I can remember this syntax. There is also git remote rm and git remote rename. In this video, we explored the git remote. In the next video, we will take a look at remote tracking branches. Remote tracking branches. In this video, we will look at tracking branches on remote Git repositories. You could view remote branches as sort of bookmarks to where the branches on your remote repositories are, or where they were the last time you connected to them. When you want to share a branch, you push it to a remote. Your local branches do not automatically synchronize with the remotes you write to. We will revisit some of this later when we talk about branching in detail. Back to our packed repository. Follow along. Type git remote show. I prefer using the -v switch for verbose output. We have none at the moment. There are two primary ways to connect to a remote tracking branch, and it is through the familiar remote add command. Git remote add master and git remote add -t for tracking and the branch name. The difference is your intent. If you need to track only a specific branch other than the entire repository, you would use the second form. Also, you can supply the -t branch name more than once to specify multiple branches. This is a bit too sophisticated for this presentation, but important to know. And finally, a little trick. Calling the git remote add with a -f switch will immediately run a fetch of the remote and create and update remote tracking branches. This is automatic, but denies you the opportunity to name the remote branches if you wish. Let's try that with our little packed repository. Make sure you have no outstanding changes that need to be committed. I have set up a public repository on GitHub for this purpose. We will use this remote repository for errata and addendum to the course. In this section, we explored the Git workflow in extreme detail. In the next section, we explore some strategies for when your development takes a detour. Often your work as a developer does not proceed quite as you anticipated. In this section, we will take a look at how Git can help when your development takes a detour. We will explore branching, take a look at branching in Git to include a bit of a philosophy around what is known as the feature branch. In this video, we take a look at the concept of branching. In an ideal world of software development, you would work on one feature set continuously from the beginning until it is complete and ready to ship. I do not live in that ideal world. My work is constantly interrupted, stalled, redirected by shifting priorities and changes in schedule. Those interruptions most often require me to not only shift my attention and focus, but change the working environment. The files, options, and loaded modules are different, or there are different libraries being used because I am asked to squash a bug that was just reported in software already shipped, and forgotten from my point of view. These diversions represent offshoots in the straight and narrow stream of my work. In other words, branches. The common nomenclature used for any source control system is a main trunk. Usually this represents the product in a working, tested, ready-to-deploy state, with numerous small branches sometimes known as trees, streams, or code lines. The advantage of branching is the ability to work in parallel on different parts of a project. This can be, as I have described, from the perspective of a single developer with many tasks, or several developers on a team each working on different parts of the same larger project. Now that we have a common understanding of branching in software development, next we'll examine how it is handled by Git. In this video, we will examine details of the way Git handles branching. We saw in the previous section that each commit has a pointer to its parent, and the most recent commit has a pointer called head. This allows Git to maintain a record of any commit's ancestry, the history. Although each commit usually has only one parent, the exception comes in the case of a merge, there is no reason the same commit cannot be the parent for multiple other commits. In essence, this is all there is to branching. The default branch name Git uses is master. When you make commits on a new repository, that head pointer to the last commit you made is considered the master branch. Each time you make another commit, that pointer moves forward automatically. When you create a new branch, Git simply adds a pointer to the current head. Then there are exactly two pointers to the same commit. When you check out a branch and make subsequent commits, that new pointer is the one that moves as commits are applied to that branch. When you later check out master, the head is now reset to the last commit on the trunk. It is important to note that branch remains as long as it is accessible. Remember, Git never forgets. In the previous video, when we dove deeply into the details of the Git directory, we saw the file named head. It contains the 40-character SHA-1 checksum of the commit to which it currently points. Switching branches simply moves that pointer. Let's actually try this with our packed repository. We will add one more commit to our current work on the master branch. This will provide a marker for us. Then we will create a branch for a new UI. We commit some more changes in that branch. This is where our boss calls and needs a hotfix immediately in the production code. We will switch back to the master, then create another branch for the hotfix. After it is tested and delivered as a patch, we will return to our regular work on the new UI branch. Now, follow along with me. Add another file and commit it. This command creates a new branch, but it does not explicitly switch us to that branch. Notice the asterisk shows us the current branch, ignoring my prompt, which was a setting in a .bashrc file. Here we will now switch to the new branch with a checkout. Using git branch again confirms this. We are merrily working in this branch. We have a deadline to complete this user interface rewrite. And then the boss calls with an urgent need for a bug fix in the production code. What do? First, we need to get back to the main trunk where that production code exists without any of our changes here working on this feature. So we switch branches back to master, and we need to create a branch for this hotfix. This time we will use a terrific shortcut. A checkout with the -B switch for branch will create the branch and check it out in one command. Remember, this simply created a new pointer to the very same commit as the head on master. So our environment matches the main trunk at this moment. We are now on this new hotfix branch. In order to fix this bug, we must edit the branching.txt file. And we must remove these empty files that begin with git. So we modified a file and deleted two other files. That looks good. Note that if we try to switch branches right now with uncommitted changes that do not match the branch we are checking out, Git will give us a warning. It's best to have a clean working state when you switch branches. There are ways to get around this, namely stash and commit amend, that are not discussed here. We need to commit our changes and we can return to our original work. This update, however, should be merged back into the main trunk, assuming they made it past testing and integration. Let's jump back to master and a quick merge. You'll notice the phrase fast forward here. Because the hotfix branch was directly upstream of the current commit, Git moved the pointer forward. It simplifies things when it can by moving the pointer forward. This is called a fast forward merge. Now, back to our previous work. The working directory is now realigned to right where we left off. We are now finished with the hotfix branch, and there is nothing of value there. It is best not to pollute the history, so we will delete the unused branch. But wait, Git has warned us there are changes that may be lost. This is because I used the lowercase d in the command. There is an important difference between the capital D and a lowercase d here. I recommend you remember to always use the lowercase. I remind myself, do not make a capital mistake. The changes are in branching.txt, and I think we can ignore them. This was a temporary branch. Let's eliminate it regardless using the capital D. Here's a place where Git will forget because we have asked it explicitly to do so. The way in which Git performs branching is quite a contrast with other version control systems that generate copies of the affected files and store them independently of the source branch. That is why branches in Git are called lightweight. A branch is actually just a reference, a pointer that moves along as you add commits. Tags are very similar too. That is the mechanics of branching in Git. But this design was driven by an overall philosophy, one which was a bit radical when Git was first created. Since a new branch is quick, easy, and light on resources, and because the branch carries with it the environment from its parent, there is a great freedom to experiment. This feature branch philosophy is captured in the idea that feature development should take place in a dedicated branch. The simple three-way merge Git uses makes it easy to merge from one branch into another repeatedly over time. This means multiple developers can each work specific features, and the master branch is not polluted with broken code, a huge advantage if you're working with a continuous integration process. As we saw in the exercise, the branch can be a diversion in your process. It may result in a dead end, but if it provides satisfactory results, you have the ability to merge your work back into the main trunk. And of course, you can pick and choose which portions of the changes to merge. With this flexibility of easily jumping among context comes the philosophy of feature branches. What we did in the exercise could also be considered a topic branch because the branch had a short lifespan and a focused purpose. A topic branch is a short-lived branch that you create for use for a single particular feature or related work. This is something rarely done with other source control systems because it's generally too expensive to create and merge branches. But in Git, it is common practice because it is so easy and cheap. In this video, we examined the feature branch and the topic branch. In the next section, we will discuss communicating with developers of the future. Communicating with developers of the future, including yourself. In this video, we will explore the ways in which the source control history is a chronicle of the life of the project. We will look more closely at these topics that have already been touched upon: history, commit messages, merging, reset and revert. Follow me on a journey exploring less of how Git works and more of how we can use it to our best advantage. Git history. This is a closer look at Git history. Recall that the Git history is a set of commit objects, blobs, and file references chained together by a reference to their parents. An engineer would call the Git history a directed acyclic graph of commit objects. There is a terrific explanation of this as it relates to source control in this book by Eric Sink. As a software developer, the Git history is something far more significant and extremely important. It represents the life of the project, showing decisions made along the way in its evolution. It has the fingerprints of every single person who worked on the project. And it becomes an invaluable reference, searchable and capable of reproducing the state of any change in any file from any time in the past. It is an important artifact. The history of Git is rarely completely linear. In other words, it does not often represent a single continuous timeline, particularly when there are multiple developers contributing to the project. As you have seen, we can use the git log command to explore the history of our repository. Like the commit command, the git log command has an immense set of options and modifiers. Here are some that I find most useful for exploring a complex history. I recommend you experiment with each of these on your repositories. You can use man git log to see them all. Viewing the history and understanding the relationships of multiple commits, branches, and merges can be quite difficult with the command line. If you are using a graphical operating system, the command git k is invaluable for getting a bird's eye view of the history. I cannot demonstrate it here on Nitrous, but here it is in a Mac. The --graph modifier for the log command creates a text approximation of what git k can do. In this section, we took a close look at Git history, specifically different ways to view it. Next, we will explore the commit message in more depth. This video is intended to challenge your ideas about the commit message and present a unique philosophy on it. When you make a commit with Git, you are required to provide a commit message. In its simplest form, this is a few words explaining what is being captured in this commit. But there is a huge capability that most users of Git completely overlook with respect to the commit message. Returning to our packed project, let me demonstrate. And back to our master branch. Here is a typical Git commit, just like the workflow we explored in section 3. Now a status to check on the index. And it looks like we have a little activity here. Good. Commit this as follows. Git commit -m, in quotes, added the commit message file. And now, for illustration purposes, add some text to that file. Add the changes to the index and commit again. And let's look at the log. By the way, the N2 limits the output to just the last 2 commits. You can put any number in there after -n, which means number. Let's focus on the commit messages. These show us what was changed in these commits, but not really why or how. Furthermore, the information these messages conveys is actually redundant. Use the diff command. You will need to apply the hashes from your output. Set the range from the first one listed to the last one. There is a lot of information here, and we will explore a bit of the detail in the next section. The most important thing here is the colored text. This shows you precisely what was changed. Remember, Git manages changes. We see the plus sign and green text shows additions, while the minus sign and red text shows deletions. Press Q to quit a long listing, by the way. The important point here is that if we really need to know what was changed and in what way, there are several ways to determine that. Putting this information in the commit message, especially as the title, is not effective. Let's explore another way, what I believe is the better way. We will back up a step. Let's work on an example that is a bit more real-world to illustrate my point. A few simple CSS files, HTML file. And here is where I may be asking you to break an old habit. We will be very particular about how we stage these files. This is only a few files intended to be only a representation of your regular work, which involves many, many files. Although the style sheets and the HTML are related, they are tightly coupled, the changes we have made are distinct. In a team, they may be handled by different developers. Let's stage the HTML file independently. And we will make a commit. But here is where we will work a bit differently. This time, the default editor opens. We have been using the -M to simplify the example so far, but now we want to be a bit more deliberate about our work with Git. First, note that the results of a standard status command is inserted by default for us. For the lazy developer, that may be enough if you remove all the comment marks. However, this does not provide you a guide as to what the commit represents. In this exercise, let's write the following as our commit message. Built HTML file for the posts page. I am using Vim, so escape V, capital G, X will remove the rest of the text. The escape : X, enter will save and close. I will capture the hash from this commit for our next step. Now the style sheets. The editor opens again. For this commit, we will enter CSS for the new post section on the main page. I pasted the hash of that previous commit. And one more. This will be a simpler one for illustration of a point later on. Now, each commit message provides a lot of valuable detail. Browsing through a large repository and searching for a particular series of commit activity is much, much easier. In these simple examples and all across the world of open source software, the trend is to make your commit messages descriptive of the change that took place without unnecessary detail about the actual files involved. This is exactly what we have done here. As a story, like a novel, this will describe the work that has taken place. But one of the most valuable purposes of a version control system is to permit a step back in time. This is restoring the state of a system at any time in the past. We saw this in section 4. Consider this from our simple example. In the first case, how would I, or any other developer looking back on the history, know exactly where to perform a checkout to restore the HTML file before we added the footer? Well, this is a very, very simple example and offers no real challenge. But I hope you see the point. There is a debate over whether the commit message should reflect what has happened or what will be the state if I check out here. I can sit comfortably on both sides of this debate. And in the spirit of compromise, I have adopted the following process. Do both. In other words, provide the descriptive what was changed, and then include a description of what I should expect to see if I were to check out at this point. There is no practical limit to the amount of text you can include in the commit message. It is really only limited to the amount of time you wish to spend composing it. If you are working on a team and use an issue tracking system, it would be sufficient to simply reference the issue number in the commit message. But I caution against that as your only description of the commit. There are tools in Git to search the history. We will see those in the later section. So be sure to include as many descriptive words as possible in your commit messages. In this section, we explored the philosophy of the commit message, and you were challenged to craft commit messages that convey important data to future developers on the project. In the next video, we will look at the power of merging. Merging. The merge is powerful and dangerous at the same time. Well, it is not really dangerous, but without it, source control would not exist. In this video, we will take a deeper look at merging and some merge strategies. There are many times you would need to execute a merge. You are always merging into your current branch. In other words, when you do a git merge, the result of the merged branches is placed on your current branch. If there are no conflicts between the two branches, that is all there is to a merge. Voila! If the work performed on the branches being merged cause changes in the same file, there will be a conflict. Git is very smart and can resolve most conflicts without your intervention. For example, changes in the same file but different parts of that file will be simple to resolve. That is another way in which Git's approach, managing changes and not simply watching files, makes it invaluable. Let's return to our packed project and construct an example of this. Recall that README file? It will be the subject of our mad science experiment. Let's take advantage of the nice editor Nitrous provides. Edit that README file. You are free to include any text you wish. For the sake of our exercise here, be sure to add a few lines after what was already there. Click Save when you are done and close the file. Now we add and commit these changes. By now this should be second nature for you. And now we will switch to a new branch. Let's call it More Text in order to easily recognize it later. Here is where we make a change that will force a merge conflict. Edit the README file again. Enter this text and be sure it is right here in the middle of the existing text. Next, change the word object to the plural objects and remove the word all here. Save and close again. You know what comes next. Add and commit. If you check the status, you will notice that lingering file branching.txt. We will ignore that for now. Now back to the master branch and one more change to the README file. Then add and commit so we can move the head pointer. Then we will merge the More Text branch changes. Aha! Git has notified us there is a conflict. In this state, we are not able to ignore this and make a commit. If we open the file flagged, our README file, you will see some strange characters inserted in the file. These are markers that show us why Git is confused about this merge. The head and arrows shows the content in the current branch. Remember, Git is concerned with contents, not files. The dashes act as a separator, and the other portion shows changes from the branch whose name is here. You fix a conflict by staging the conflicted files, adding them to the index in the form you want. In this case, that would be correcting the README to be what we really want it to be. But first, let's explore a few other tools Git provides to help you when that crucial and complex merge conflict arises. Diff will show the differences. Each file is represented by a letter, A and B here. There could be more. The plus sign represents additions. This shows us the number of lines added. Likewise, the minus sign shows the lines removed. This line of text shows us exactly where those changes are in the file. And then the changes are highlighted with red for deletions and green for additions. The white text is there to provide context as a sort of an anchor. Notice this also shows those merger markers as added in this file. And we have differences in the branching.txt file between what is in the index and the file's current contents. To view the file contents before the conflict was detected, use git show branch name : file name. Then we have git ls with the -u switch to show us changes that need to be merged. The U is for unmerged. These are the blobs we talked about in section 3. Each line represents a different version of the file: common ancestor, current branch, merging branch. Finally, using the numbers displayed, we can see each different version of the file with git show colon the number colon and file name. Let's change the README file to be exactly what we want. A lot of text here. That resolves the conflict. Now we stage the changes and commit. The Git log will show us this commit. This was a simple merge, but it is important to note Git will support merges of more than 2 branches. That is a topic beyond the scope of this particular presentation. Before attempting a merge, you can use git merge -- no-commit, more text. This shows the result of the merge without making any commits or changing any files. That was a detailed look at the merge in Git. In essence, when Git sees a conflict, it drops those changes from the index, alerts us of the problem by marking the files, and waits for us to make another commit that represents our true intent. Generally, Git does a good job of merging without consulting the human user. Recall what we said earlier about Git history. Each merge forms a new entry in the history. We just explored the merge in a very simple example. As you build confidence and experience with Git and merging, I trust you will become more proficient with more complex merge situations you encounter. Next, we will see how to undo in Git. Reset and revert. When you find yourself saying oops or something worse, what do? In the words of Douglas Adams, first, don't panic. In this section, we will see that nothing you do in Git is completely irreversible. You may have read numerous entries on Stack Overflow advising the use of Git reset. The default behavior for reset is discard the commits but apply no changes. Adding the --hard instructs Git to rewind and apply the rules from those commits. The index is also cleared. You end up with the same state as when you originally just made that commit. In the packed project, let's create another file. Add it to the index, and we see it is staged for the next commit. Now, suppose we had a change of mind about this. With Git reset, it is as though those staged changes never occurred. Let's look at the --hard option. No fear, the history is not lost. Git log --all --decorate --one line is really handy. All we have done is reset the pointer for head. Another way to view this is with git reflog. This is only local. It represents your interaction with Git. Git log --one line only shows what is in the current history on this branch. But those commits still exist. Add the -g from the previous section, and we get a whole log of information. The fundamental difference between reset and checkout is how the index is affected. Be careful when using reset on a shared repository. Never reset any changes that have been pushed. Some files need to be modified that are already in the pushed repository. Similar to reset is revert. Revert undoes all the changes in that particular commit and then adds a commit. It is a super undo. If you need any of those changes or files, they are still in the history and can be recovered. Git rebase is a very sophisticated command. We will only introduce it and touch on the most common applications for it. In a rebase operation, Git walks back through, rewinding all the commits back to the one we specified, and unwinds each change. We examine this in more detail in the next section. This is handy after a long series of work to get a bug completely resolved. The history can be cleaned up, and you look less like you were fumbling around to fix the bug. Among the options we have just explored, revert is the safest way to undo. It generates a new commit, and you can write a message that explains and adds it to the history. This also protects any pushed changes. In this section, we saw less about how Git works and more how Git can help us do our work. In the next section, we will explore changing and managing history. Changing and managing history. In this section, we will explore even more related to the history, including a few really useful utilities that are part of Git. Altering history. The history is a vital part of the repository. It could be argued that the history is the essence of source control management. In the previous section, we explained the importance of the commit message in telling the story represented by the history. There are times you would like to modify the history in order to better tell your story. Here we will explore the tools that permit you to manage and manipulate the history in order to better tell that story. Let's begin by looking again at the rebase command. Rebase. We looked briefly at rebase in the previous video. It facilitates rewriting of history, reorganizing it actually. Until you become very familiar with it, rebase is one of those scary commands. The easiest way to become comfortable with rebase operation is to use the interactive switch. This allows you to be very selective about how Git applies the changes. Git rebase generates a sort of script file that represents all the commits derived from this one. By editing this command file, you instruct Git how to rebuild the history. It displays all commits in reverse order, oldest to newest, because we are rewinding the history. We will try a very simple exercise. Let's go back to our Pact project and get just a little hands-on practice with this. Remember, I am using Nitrous for these exercises, and if you also use Nitrous, your environment will be the same as mine. If we look at the branches, we see that new UI branch we created in section 4. Let's test and see what would happen if we merged that. And we are advised all is well. But if you look at the log, there was no commit performed. So let's complete the merge. And we see the merge in the log. A rebase would allow us to apply those changes made on that branch directly on top of the history. Let's explore how that would be different. First, we need to create a new branch and add a few commits. You should be quite comfortable doing this, so I will go through it very quickly. Create a file that is only in this branch. Add it and commit it. And let's make this branch noticeably different from master. And finally, include that lingering file, branching.txt. Now add the new file and make a quick commit. And now we need to increment the history on our trunk by making some dramatic changes. Let's clean up some of these files. By the way, you can list multiple files for almost all commands where Git takes a file spec. Lastly, we will add some more to our README. I encourage you to continue using this to include notes to yourself as you gain experience with Git. And we need to add those changes. Now, a simple commit. Now we will lay upon the current head the changes that branch represents, like this. One peculiar thing to bear in mind is that unlike the merge command, Git rebase requires you be on the branch you want to move. We see the two commits on that branch. I admit this is a very simple example, but that is a great way to gain confidence and practice by working with small, simple exercises. If we save this as it is, the entire branch will be rebased onto the master. I encourage you to experiment on your own and try each of these options, particularly the squash and reword. I use those quite often. Let's meld these two commits into one with the squash command. Lastly, I want to point out the text at the bottom. You can rearrange the way the rebase will behave by reordering the lines. That is a quite powerful capability, and you can be confident that Git will do all the work to apply the changes appropriately. And here we can craft a good commit message. Voila! Notice how the newly formed commit was applied on top of the history from master. Finally, we ask Git to perform a fast-forward merge, which does not generate any more commits, but merely moves the head pointer. And we can delete the branch. Remember, that is only a pointer and is now irrelevant for us. This is what we did with the rebase operation. After the rebase, the feature branch's parent commit is the same as master. In our case, we squashed two commits together into one as part of the operation. Instead of a merge, Rebase integrates the feature branch building on top of the master. This provides immense control over the history, and we can rewrite it to be more linear and tell a better story. Next, we take a look at Blame. Personally, I think the name for this command is a bit rude, but I want to believe it was developed with an air of humor, a bit tongue-in-cheek. Its purpose is to isolate the point in history where a particular change occurred. Usually this is to track down the introduction of code that causes a bug which is not discovered until later. The intention is not to point a finger and place fault on one particular developer, but rather to pinpoint a specific commit based on facts known about the trouble you're investigating. I see Blame as a specialized filter on the history because it will show all places a particular file had changes committed. Here's a clone of an open source project called exorcism.io. Let's issue the blame command on about.erb. Notice this does not show us commit messages, but actual changes made to the file. The last change made and who committed it. But you can check out any of these commits by their hash and investigate further. And with a -s switch, the name and date are suppressed. If you really don't care who did it, that is enough blame for me. Let's now take a look at the diff utility. We saw diff in the previous section. Here I want to explore a few details of this handy utility. The simplest and most common usage is to compare the current working tree with a commit. The commit is usually the head, and so the command is just git diff. This is useful to see the state of your working directory compared to the index. But diff can be used to compare any two commits. As a matter of fact, you are not limited to only two. And if you want to examine the changes that took place between two commits in the history, use the two dots like this. In a more complex Git history, there is an important difference between using two dots and three dots. Simply put, the double dots is a direct comparison between the two commits, whereas the three dots shows a diff between the first commit's base and the second commit. What not many people realize is that git diff can also be used to compare file paths. Just use the no index switch. If you wish to try this on your packed project, the hashes will be different than I have here, so adjust appropriately. Lastly, a really handy trick to examine the entire set of changes over a specified period of time is this. Utilizing the git log with a few simple options to define a time period and reverse the listing, and then piping the output into git show. This is only available in Unix-based systems. This is not supported in Windows, I'm afraid. Now, let's look at a more magical utility, bisect. Bisect guides you through a binary search of the history, asking along the way for you to identify commits as good or bad. It is similar to that child's game, Warmer, Colder. Let's suppose you have a bug that crept into your code. If you knew which file was causing the problem, you could use the blame command, as we just saw, and locate the exact commit where the problem was introduced. But all you know is where it works, as expected, and where it is broken. But that is enough when you understand how to unlock the magic of Git bisect. The steps to using Git bisect are very simple. Tell Git you are beginning a binary search for a bug. Git bisect start. Designate a commit where you know the code is good. Git bisect good and the hash. Designate a commit where you know the bug exists. Git bisect bad and a hash. Repeat as necessary. Exit the binary search with Git bisect reset. Let's try it with our packed repository. We don't really have a bug, but we can pretend in order to get some practice with this process. Browsing the history, let's just pretend we know all was well back here at the commit with updated readme as a message. So I will take that hash, use the one you have, it will be different, and use it for the Git bisect good. We know the bug appeared just recently, not long after we performed that rebase with the topic branch, so we will take that very last commit. And so we can inspect the state at this commit. This is where we changed some text in these headers. Let's say the bug still exists here. Of course, with real source code, you would run or compile this and test it. We are being a bit arbitrary for example's sake. So we call this bad. And here the README looks good. We will call this good. And this looks good too. We will tell Git so. And magically, Git shows us the blob object, the change that introduced the bug. We have isolated the problem. Now we can stop the bisect operation. Note that no changes were applied to our repository or working tree. This was strictly an investigation of the history. But Git acted like an amazing detective, helping us track down the precise commit that tipped the scale to introduce a bug. That all appears a bit magical. But with a better understanding of how Git stores, manages, and tracks changes, it should be a little less mysterious to you now. Next, I would like to introduce you to patches. Patches. Another way in which Git shines over many other source control management systems is the way Git can generate a patch. In essence, a patch is just a set of changes from one point in time to another. As we know, Git manages changes, so it can perform extremely well here. Those changes can be distributed in a lightweight package, usually attached to an email message. This was far more popular before the days of the internet, when email and FTP was the only means to share files. The patch can be a single commit or a version range. Back to our packed project for a quick and simple exercise. Let's suppose we need to send out those changes we made for the new UI to another member of our team, and for some bizarre reason, the only vehicle is by way of an email message. For the sake of demonstration, I will inject a bit of text into this file. Stage it, and a quick commit. We now have a few commits on this feature branch. We would define specific commits to include in the patch, and we would need to do that if we were deriving the patch from master or wanted to take just a small set of commits. But here we applied the preferred practice of placing all our work in a separate branch. Another example of the importance and power of feature branches. For that reason, this operation is as simple as this. The --std out directs the output to standard out. We can look at the status of this patch with the apply switch. This is what the recipient would probably do first. Then apply the patch with git apply. This does not create a commit, however. Let's take a quick look at the patch file. It should be quite familiar to you. Notice the file is formatted as an email message, including the sender address. This was taken from the global configuration we set up in Section 2. Lastly, we examine Git submodules. A Git submodule is a Git repository that resides inside a project repository. This is useful when you need to include some other software, say a library, in your project, but don't want to maintain custom changes or lose the advantages of updates made to that project. Now, that project is under a subdirectory in your project, but as a submodule, Git knows to not track that directory's content when you are not in that directory. It is treated specially. You can work in that directory, make changes, add a remote repository to push your changes, fetch, and merge from the original repository. Submodules are a bit tricky, and you must be careful when using them, particularly if you clone a project that contains submodules, because Git is tracking the specific version of that submodule. The submodule directory will be there, but it is empty. You must run these two commands in the submodule directory in order to get the right version of the submodule: git submodule init and git submodule update. Submodules is yet another feature of Git that is underutilized. Perhaps it is simply not well understood. The large team working on Git also use it to manage the project. That provides them an immense advantage in that they know what feature and operations would be valuable to the users of the software. All these utilities grew from a need when managing projects like Git itself. In this section, we explored many of the more advanced and perhaps more mysterious utilities in Git. My goal is not to make you an expert, but rather make them seem a bit less intimidating so you are encouraged to use them on your projects. In the next section, we will see a few more ways to apply the features of Git in your daily work on writing software. Getting more efficient. An introduction to various techniques and shortcuts to improve the efficiency of using Git. We will take a look at stash, aliases in Git, and GUI clients for Git. Stash. In Section 4, we saw how branching can be used to divert your workflow on a project when an interruption is thrust upon you. In that case, a bug was part of the main trunk, just a few commits prior, and creating a temporary branch was an effective way to attack the problem. But what if you need to make a fix on something that lives on another branch? You don't want to abandon your current work, or suppose it could cause a major problem to commit your work unfinished. What can you do? It would be great to just take a snapshot of your current working state, clear out any changed files, and jump to another branch to work on some different problem. But making a commit here would really mess up the history that you were working so diligently to keep clean, clear, and concise. Well, this is what Stash was made for. Stash takes you back to just before any of the changes you staged. In other words, back to a state that matches the last commit, the pointer head. But it also makes a special commit of any staged changes. Back to our packed project for some practice. To our favorite new UI branch. For this exercise, we will make the working tree a bit messy to emulate work in progress. First, we will modify the file branching.txt. Then stage these changes and make a simple commit. At this point, switching branches would be no problem because our working tree is clean. But suppose we are right in the middle of some work. Let's make some more changes and stage them. And then leave some files in the working directory that are not staged. This is a very simple and contrived example, but it properly illustrates a messy working tree in Git. Some files whose changes have been staged and others in an altered state but not staged. But we have an open-ended commit here. README is staged and default.css has changes that are not in the index. Hold this concept in your mind for a moment. We will be right back to this. And the boss calls again with an emergency change that needs to be made in the more text branch. If we merely switch branches, our work in progress will be lost. As a matter of fact, Git will be sure we do not make a mistake like this. In the rare event this is what you really do want to do, there is a force switch you can use. This is where we can use stash. First, notice the head now points to the last commit we made, and the files are still there, without our changes. Now, let's jump over to the more text branch. There is no difficulty doing so now. While we are here, let's make another pretend bug fix. I only wish my real job was this simple. A few important changes here. A quick commit. That fixes the bug. But I have intentionally left this one dangling change on the commit message.txt file. I want to use this opportunity to demonstrate some more about stash. Let's stash this working tree now too, and then return to where we left off. Now to restore our working state from the stash. But notice the status. Recall that we had staged some changes for the README file. This is the default behavior for stash apply. If we used the -- index switch, then the stage changes, the index, would also be updated to match what it was when we made the stash. Let's see how that would work. I hope you did not lack confidence that the staging information was still there to be retrieved. Git never forgets. Let's commit these changes. The command git stash list will show us all the current stashes. Notice that these are really commit objects, and the default name includes the branch you were on when the stash was saved. There are a few additional commands for manipulating and managing stashes. We had some experience with save, apply, and the -- index switch. You saw how to list all the current stashes. You can clean up by using drop, and even take the contents of a stash and make it into a new branch. Git stash allows you to temporarily put aside some unfinished work. You can then check out other branches, make commits or changes, get that bug fixed, and merge or rebase the branch. And when you're ready to get back to where you were, just type git stash pop, and like magic you have returned. The really important thing to remember is that stash will only preserve files in the working directory that are being tracked. That means they must be in the index. There are times when you perform a pull operation, and due to a conflict in your working directory, Git refuses to merge the upstream branch. In this case, you can use stash, which cleans up your working tree, pull, and then use stash pop to bring your current state back in focus. In the next video, we will take a look at the Git alias capability. Aliases. Alias is terrific for many of the Git commands you find yourself using often, or in my case, those you often mistype. In the global configuration of Git, we can define any number of shortcuts. Here are a few I use often and often mistype. And then Git will recognize the alias. What is even more exciting about these is that even when you mistype an alias, Git will offer you some help. There is a section in the git.config file where these are all maintained, and you can add or modify them directly by editing that file. You can maintain your library of Git aliases by editing the alias section. Here are a few for fancy log output. Call this with -P to see the lines that have changed. A slight variation on this theme is this one. This alias will remove branch references that no longer exist, clean up unnecessary Git files, remove untracked files from the working tree, clear out your stash. And as we discussed stash, here are a few shortcuts for stash. Of course, the only downside to these is A, you need to remember the new shortcut commands, and B, if you are pair programming with someone who does not use the same shortcuts, or none at all, you can feel suddenly crippled. That neat trick I pointed out in section 6 can be simplified like this. And finally, to list out all of your aliases, use this. The alias definitions I described here are in the Mastering Git repository for this book on GitHub. The URL is in the final part of the presentation. In the next video, we will see what is available for graphical user interfaces to Git. GUI clients for Git. We have been focused on the command line, and I firmly believe there is a lot of efficiency that can be gained from it. I am a huge fan of the command line, but acknowledge that sometimes it is easier to manipulate groups of files or visualize a complex merge with a graphical user interface. Here are a few of the more popular choices. Git for Windows is built on msysgit by the brilliant people at GitHub. This is a good all-around tool for Windows users of Git because it offers command line bash emulation, integrates with the Windows shell, and has a fully graphical interface for working with Git. GitHub for Mac and GitHub for Windows are free and include great integration with GitHub. Push and pull operations are simple and transparent. They are called synchronized. SourceTree is another very simple and elegant tool and is available for Windows, Mac, and Linux. Git-Cola is written in Python and an open source project. So if you like the Python language or wish to have some input on building the tools you use, you will enjoy this. It is also available for Windows, Mac, and Linux. SmartGit is available for Windows, Mac, and Linux, but it is not free. There is a long list on the Git Wiki site. As with so many things in life, it is far more valuable to first learn the fundamental operations of something before utilizing the shortcuts. But software ultimately is intended to simplify our work. A good GUI client can help make working with Git much smoother, and I recommend you try some of these for yourself. We saw a few tools to help make us even more efficient when working with source control. In the next section, you will be launched on your way as an accomplished Git master. It has been quite an adventure, and you have taken a journey through lots of concepts, ideas, opinions, and command line options. At this point, you should feel far more comfortable using Git than when we started. Perhaps rather than asking a colleague for advice, you will become the one everyone else comes to when they are having trouble using Git. I hope you've taken advantage of the opportunity to sharpen your Git skills with practice along the way. We began with a repository with a single README file. That was a great place to add notes and ideas as you gained knowledge and experience with Git throughout the course of this presentation. With this increased knowledge and confidence, you will travel unafraid into more complex problems and solutions with Git. In order to continue to help you along this journey, I want to share a few of the more common problems you are likely to encounter when trouble arises. For most, I will offer a solution. For some, I will challenge you to reason out the answer on your own, or even better, hack at it with a Git repository. The lessons we learn when puzzling through a problem on our own tend to be more permanent. We will look at a few topics: working with remote repositories, remote branches, changing commits, garbage collection. Although Git is a decentralized system, cooperation on projects is often done through a common hosted service. Using the Git protocol requires SSH connectivity. When troubleshooting connectivity, there are a couple of useful commands. Using the -t switch with the SSH command can provide a quick test of the connectivity. If that fails, you can add the verbose command. There is a great little set of instructions on the GitHub help pages. You may find that when attempting to push your changes to a shared repository, you get this message. It is likely this occurred because someone else on the team made changes since you last pulled from the repository. As we have learned, you could use git fetch, try to merge the changes appropriately, and move on. Or you can simply use this command. Then you can confidently push and continue your work. Remember that pull is really just a fetch and then merge, so this is an immediate indication your local changes are not based on the latest commit in the history. When this situation arises, I recommend you exit the editor and abort the merge and use the rebase method we just saw a moment ago. Remote branches in Git. It is important to understand that you cannot interact directly with remote branches. The refs to remote branches are only pointers to where the branch was when you last performed a pull. In order to interact with a branch, making commits or pushing, you will need to set up tracking of that branch. Using the -a switch shows all branches. The only tracking branch is master. You can view the remote branches with git checkout. Notice we are in detached head mode. We could check out to a new branch. Notice the success message. But this simpler syntax will set up the remote branch too. We use the very verbose switch again. Deleting a remote branch is something you will likely not do often. Here is the very strange syntax for this. In essence, you are pushing an empty branch to the remote ref. Changing commits. The commit command with --amend will open your editor and permit you to edit the commit message of your last commit. You can also use the -m to accomplish this on one line without opening the editor. Git rm file name will remove the file and tell Git to stop tracking it. But if you simply want to take a file out of the index without actually deleting it, add the --cached switch. Remember, when using git reset, the --hard will update your working directory to match what is in the index. In other words, any changes you may have in the local working directory will not be preserved. Undo the last commit. Maybe you forgot to include an important change or made a serious error in the commit message. Git reset --soft head ~1. This will restore the working tree to where it was just before the last commit, as if that commit never occurred. But as we know, this only resets the head pointer. The actual commit object will remain, and you can see it with git reflog. It remains until you use garbage collection. Like any database, as a Git repository grows, it can accumulate lingering artifacts and dangling commits, specifically commit objects and tree objects that simply have no relevance anymore. Git has a garbage collection scheme that is activated automatically, but it is very, very conservative. You can, however, initiate the garbage collection process. Starting from the tip of every branch and from every tag, Git walks back through the graph, building a list of every commit it can reach. Once it's reached the end of every path, it deletes all the commits it did not visit. Let's try it on our packed project. Next, we will reveal your personal help aid, the ultimate reference. We have compiled a Git repository that contains the essence of this entire course, the exercises plus some additional content I could not include at the time. It is hosted on GitHub and is a public repository. If you have comments, updates, or corrections to errors you have found, please utilize the issues here. I gladly welcome pull requests for corrections to errors or additional data you wish to share with others who use this course. Perhaps you found a better way or some handy resource. You can pull this repository and use it to hack on, practicing and gaining some confidence with those scary operations we discussed. If you have taken notes along the way, you will be able to practice your Git skills by performing a merge from this remote repository. This is my gift to you for your patience, persistence, and attention throughout this presentation. The next section is our epilogue. Final thoughts. We have discovered and discussed in detail quite a lot about Git. Never again will you panic when something seems to have gone wrong when working with Git. Never forget these simple principles. In the previous section, I revealed the Mastering Git repository on GitHub. Check there first for errata and addendum. You can practice all the techniques we discussed safely and without fear using this repository. I welcome pull requests with your own enhancements to this course. There is also a wiki, which I hope to populate with tips, tricks, and ideas that you submit. You can also clone a repository from GitHub or Bitbucket, any repository, and use it for practice. You need not push your changes. You needn't even keep the repository afterwards. In this way, you can experiment with a repository that contains numerous commits, branches, merges, etc., with no fear of breaking something important. You can be confident diving into some of the more complex areas we discussed here, like Rebase and Bisect. Changes in Git version 2. Changes with the new Git. At the time of the creation of this production, the long-awaited Git 2.0 has just been released. If you've been using Git for many years, there are a few significant changes you should note. The first one we saw in section 3 with the way in which Git add now behaves. You can configure it to act like previous versions if you prefer. Changes in Git add when you do not specify a path spec. Git assumes the entire tree even if you are in a subdirectory of that tree. The git log command has an additional show linear break switch, which is very useful. I recommend you experiment with this on your own. Changes in the git pull and push. With pull, you can specify a preference for fast-forward merges. With push, you now need to be a bit more specific about which branch you are pushing. And the git ignore file is a bit more strict. As this update says, it should not affect you unless you were being a bit sloppy in your entries in the git ignore file. Congratulations! You are capable of managing your source control a bit better than most others. You have confidence in your abilities to use Git. You have confidence that Git will not destroy or lose your work. You now have a bit more confidence when approaching a problem with source control. You are no longer intimidated by Git and its slightly arcane syntax. You will be recognized as the one who has the answers when others are struggling. If you have enjoyed this presentation and found value in the information provided, I encourage you to share it with your circle of colleagues and friends. Brag a bit on social media about your new status as a Gitizen, part of the community of Git Masters. There is a badge you can use on your website, in social media, in online forums. Above all, it is my sincere hope that the information here has helped you to grow. Also, don't miss the wonderful array of other great books and videos Pact Publishing offers. In this video, we gave ourselves some well-deserved credit for completing the training. In the next section, you will find a list of resources and references to help you continue sharpening your skills. references, and resources. In this final section, we will look at a list of resources to take your learning further. First, a few little nuggets of information that would not fit neatly into any of the other sections. When we looked at the git add command in section 3.2, I made a passing reference to the -I switch. This permits you to selectively choose which parts of the changes will be staged. It is very handy when you are working on a particular problem and fix something else unrelated along the way. That other thing can be left unstaged so it does not pollute your history. As we know, git status shows what files have changed and/or have been staged since the last commit. With the git diff command, we can see other changes line by line. It is generally good to use these two commands in succession. With git diff -- cached, you will see the details of the staged content. This will show you the changes that will be captured in the next commit. If you loaded the set of aliases from the mastering git repository, this command can be called as git dc for diff cached. The git reflog shows all the commits regardless of their connections. You can use it to locate anything, including blobs and files. The git fsck with the unreachable and the lost plus found switches is also like gold. Throughout this presentation, you may have noticed my bash prompt always displays the current branch when I am in a directory with a git repository. The bashrc file contains this little bit of code. With this, the current git branch is displayed in the prompt. This is in the mastering git repository. Here are a few references and resources that have helped me in my quest to increase my proficiency with Git. This is a description of Git operations, specifically how branch, checkout, fetch, pull, and push work. As he states in the beginning, branching and merging are central to effective use of Git, and if you are not comfortable with them, you won't be comfortable with Git. A comparison of protocols offered by GitHub, better understanding of diff, a great explanation of the internal storage of objects and trees in Git is in ProGit. An interesting use case for Git submodules. A good reference to explain merging. A good description of feature branch workflow. Git from the bottom up. I encourage you to add some of your favorite resources to the Mastering Git repository with a pull request. Acknowledgements. I need to say thanks to a few people whose contributions and assistance was critical to the success of this project. Matt Parkin applied his great skill as a digital artist to generate many of the graphics used throughout this video. I am grateful for that and for his continued dedication as a faithful son. Thanks to Jacob Hoffman for validation and testing of some of the ideas and the code. Thank you, old friend Rich Hireling, for the photo of you in the Darth Vader costume you made in the 1970s. I wish to say a big thank you to Pact Publishing. When they approached me with the idea for this project, I had not yet created something quite this large and extensive. The careful guidance and obvious experience of Hardik and Madhura made the process smooth and enjoyable. And thanks to BGit for providing a magnificent platform for authors which is built on Git. It is only fitting that I wrote the outline of all of the scripts for this presentation using BGit. The great people at BGit are offering a special bonus just for you. If you subscribe to BGit's terrific service and enter the coupon code MasteringGit, no spaces, you will get a special discount. This presentation is nitrous charged. All the exercises were developed, validated, tested, and recorded using nitrous.io. This URL provides a good introduction and overview of nitrous.io. Thank you for watching.